I know.
Hey.
I don't know, I'm getting.
I forgot we did. All right, we're gonna get started. Announcements, we're not doing too much at the moment. I assigned an assignment last week that is gonna be due a week from Wednesday. As we are starting to see from the people who have had a chance to get started on it, it is long and complicated, and you should not wait to start that until close to when it is due, or that will be painful. So get started early, come see me and talk to me if you have questions. There are plenty of pumping lemma on that, so you will probably at some point need to talk to me, and we'll have some kind of intuitive conversation about how to solve the problem. And we'll go from there. But yeah, don't put it off to the last minute and hope that you can scrape your way out. It is going to be a very challenging assignment. It's worth a little bit more than the last couple of assignments. I generally just like to say 10 points per problem and not try to figure out how difficult each problem is. That said, there were 24 problems on this one, so it will be a little involved, especially since some of them are long pumping lemma problems. Questions before diving into new content for a while? Nothing else on the horizon. I will try to get exams turned around to you by Friday. We'll see how that goes.
And if you're gonna cover this, I apologize. What are some examples where you can't rewrite a language to remove ambiguity?
Yeah, so there will be some cases where you try to do that mapping, and that is difficult. But so some examples of which part of this exactly?
What are some examples of grammars where you wouldn't be able to rewrite them?
Oh, you can. It says that can often be rewritten. Yeah. So if you're, it takes a particular kind of setup, but you can show via induction that if you were to rewrite this grammar, then the ways that you can rewrite this, if ambiguity is present here, then ambiguity will be present here for some reason, and you show that for every way that you could expand the grammar. I do not know off the top of my head what the uses, like the use cases, what would be great if we could rewrite a particular, what would that allow us to be able to do? I don't know that off the top of my head, but that would be a cool question to answer for sure. If someone dives into that hole and finds an answer, let me know. But we'll talk about how to recognize ambiguity and remove some ambiguity, but it ends up being a really complicated question. It's been a hot minute since we talked about this. So summarizing, we talked about grammar ambiguity. This was the concept of we have two different grammars that represent the same underlying language. However, we can produce at least one of those strings with different paths through that grammar. There's no one path way to produce a particular string. We can get there from a couple of different ways, and that's not good. When we talk about compiler construction, we want there to only be one way to generate a particular result. We talked about this grammar, which was very interesting. So we talked about this allows us to be able to make parentheses, multiplication, and addition. The question I left you with is there an order of operations to this grammar? And the answer to that was this doesn't really force any kind of order of operation. Yeah, it's pretty undefined. So we restricted to variables, and we found that there was not too much to the order of operations. The question that I had for people was, what could we do to enforce an order of operations? Does anyone think they have any kind of answer to that? How would an order of operations become present in a grammar? Yeah.
You rewrite some of these productions so that certain expressions are only available after or before doing others.
Yes, that's exactly right. We need to have some kind of flow through this grammar where we can produce, we force the lower precedence, and then we can expand the lower precedence into higher precedence. And that means that the deeper down into the tree you get, the higher the precedence of the order of operations, because we're thinking of doing something in a depth first search order. What is the first, what's going to be evaluated first? And that's what's deepest in the tree. You need the results of what's deepest in the tree to create the variables for what's shallower in the tree. So that means that we want to be tackling that deepest. So we see that the prior grammar is ambiguous when we break this down into how do we evaluate it? Well, we could either come up with the plus first and use that, or we could come up with the times first and break it down based on that. So looking back at A plus B times C, let's actually just look at the grammar. Let's say we actually have that. We want to be able to generate A plus B times C. So we could say that we start with an E, right? We want to say this is some expression. What do we want to define that expression as? Well, we can think of there's something plus something, so we can either break it down here, A plus this quantity B times C, or we can come up with the quantity, the left side times the right side, A plus B times C. And this grammar lets us do both of those first. So depending on which one we choose, we end up with being in one case or the other, where we can build both of those different parse trees. So now you see this expression somewhere, and if these are the rules, it's the grammar that you're following for those rules, there are now two different ways to evaluate this expression that could give you different results. And that is not good. We don't want our math to be ambiguous. That breaks logic. We need an order in order to have one answer to every expression. So here are those two different parse trees, and you can see that how this is generated, or how you would see this, is again a depth first search order. So you would just read A plus now the quantity B times C, or we would have A plus, we can get B out of all of that. So we'd be evaluating A plus B before we multiply by C. Does everyone see the depth first order and how that creates, in order to answer this problem, we have to evaluate this. This won't be known until this whole expression is evaluated and ready to give us this value that we can use the addition on. So we would do this expression and then that expression, or we would do this expression and then that expression. Questions on that? Does that make sense?
So the one on the left is the correct one that we would want to do.
By default, yeah. Yeah, so how would we enforce that? We would want to say that this construction is legal and this construction is not. We would need some way of modifying the prior grammar to disallow this. But still be able to compute that particular value, but you would be forced into using parentheses to do so. So we, of course, can just rewrite the grammar to follow those rules. Does anyone want to take a stab at trying to come up with a grammar that does that? You take a few minutes, see if we can figure out what it would take in order to get that and force that precedence. I think that's worth spending a few minutes on. Yeah, so we're gonna go take a look at this, and now spend some time, talk to people around you. And what would you do to encapsulate precedence and order of operations to force any multiplication to come before addition unless there are parentheses? What's the flaw in the grammar that's preventing you from doing that right now? Yeah.
It's evaluating to three different
Yeah.
operations.
I think we're gonna need some different non-terminals in here to force the order through those non-terminals. So that is where you should start.
parentheses, just cross board.
That is an interesting idea. The question is, where do you put your parentheses?
When you make the multiplication or the addition, you just
Yeah.
have to put the parentheses around whatever you're working on, so that way you have to create some.
How do you do? How would you know? I think you're still gonna run into that issue. Even if you put parentheses around everything, the question is, should there be parentheses around this individual E? Because when you expand it out, you get something like A plus B times C. You wanna be able to override that with parentheses, and if you force parentheses into it, then I don't think you can evaluate
You just have to
any exception to that.
make the, if you wanna do addition before multiplication, you have to do what you're doing. What
Yeah,
you're suggesting, where you put that on the inside, if you wanna do the other way
If you
around.
make the parentheses optional for everything. But this is kind of forcing those parentheses to be optional. We can either see them there or not. So I think we just need to set up that precedence. Because all of this logic is basically there. It's just a matter of, this does say parentheses are optional. But I think we can do it by just changing the non-terminals.
Yeah.
Anyone have something they think might be correct? Or at least involves or should be looked at deeper? Yeah,
I mean, it's a messier way to do it, but instead of having E that's repeatable within the expression, like E times E, we have a different variable then, like be something like A for like the day, just for some mnemonics. So now we
Okay.
have an A, or A can also now have, something like parentheses within it, or it could also be I, so it can turn.
okay, interesting. Let's take a look at a solution. I wanted people to start thinking about what would you do? What road would you go down to try to make this a thing? So the answer is something like this. We're going to define two different non-terminal or two different productions that we can use for E. E can either be an addition, or we can directly go one step up the precedence chain to make it, all right, let's look at multiplication. That is the T. So T can either become an expression that is multiplication, or we can go up the precedence chain to putting parentheses around a particular expression. So this allows us to map E to T to F. And now F can guarantee those parentheses, but now in order to do a multiplication, we have to go through the addition such that each one of these components, E and T, can be the addition. If we're going to recurse the addition, has to come first. Otherwise, we have to get at least multiplication on the second part, or to go directly to become multiplication. I don't know if I explained that particularly well, but there is a path now to produce one and only one type of solution for the expression A plus B times C. Let's take a look at that with this example to see what's happening. So if we want to produce A plus B times C, we start with that same expression E. So we can either, we want to produce this E plus C because we need that. There's going to be multiple parts to this expression. If we went down the E to T route, then we could only generate the second part, the multiplication. Once we get some multiplication, we can't go back and put some addition before that. This T times F says none of these can be E's that it would involve addition at all. So we need to start by focusing the highest up portion of this tree on the least precedence model. If there is addition, you must start there. Unless you're overriding the order of operations, in which case you would utilize the parentheses to force down to override the order of operations. Once we have that E plus T, now we can go straight down the chain to produce the A. Since what's remaining now is just the multiplication, it's okay, this E can become that T, which can become the associated multiplication that we need to go back up the chain to produce the B, back up the chain to produce the C. There was no way people were gonna come up with this in a short period of time. Don't worry about it. But I think that the important part here is understanding how a grammar in this form that forces a particular order, you start with the lowest precedence and work your way up to the highest precedence. Via some sequence of non-terminals, we define just what that process looks like, and then force the additions to come before the multiplication. We must evaluate an addition higher up in the tree, which means what's going to happen first is what's lower down in the tree. So we need to evaluate this multiplication before we have the value of this t for this addition. Since multiplication should come before the addition. Any questions on that? That makes sense? So if two grammars are equivalent, difficult to show if it's ambiguous. We actually don't have an algorithm that can always answer whether a grammar is ambiguous or not. It's an undecidable problem, unfortunately. We'll talk about exactly what that means later on in the course. But if we can find an example, then we have it. It's just that there are an infinite number of strings in these languages, so we can never answer the question. Yes, I've looked at 20 billion strings and I'm able to generate all of them with both of these. Does that mean that these grammars are equivalent? No, it just means I haven't found the example yet for why they're different. Or if none of those exists, then you can't ever find that. So answering equivalence can be really challenging. So we go from talking about ambiguous grammars to ambiguous languages. Sometimes the structure of the ambiguity is just baked into the language that we are talking about. There is no way to remove the ambiguity from the language. Let's give you an example. Here is a language. A to the n, b to the n, c to the m, union a to the n, b to the m, c to the m. So this is the language where all the a's come before all the b's, come before all the c's, but either there are the same number of a's and b's, or there are the same number of b's and c's. The first question I might ask you, is this a context-free language? Can we build a grammar that represents this language? Let's give that a try. I think that's good practice. Context-free grammar, no rules associated with simple grammars or regular grammars. You have the full power of the right side of your production can be any number of terminals or non-terminals in any order. How do we do it?
Starting state, enter one of the two ways.
Yeah, that's exactly right.
Then from there, you would have it expand with, on one side, you know, whenever you have an expansion of an A, it's A, B, and then
Yeah,
continue, and then that can either be a B again or a C, and then from there it just makes C's. And then on the other route, then it makes A's and
Yeah.
then it's B's.
Yeah. So here's the left side of the union. We say from the starting state, we can produce an arbitrary number of C's. Once we've produced as many C's as we want at the end of the string, then we transition to a non-terminal where we're producing an even number of A's and B's, recursing in the middle. Whenever we're done with that, we terminate. And that would give us A to the n, B to the n, C to the m. We can have an arbitrary number of C's And then we hop in and produce the same number of A's as B's. The right side of the union. Oh no, like I did this wrong. Real quick, I will. That's funny. A very fast fix. There we go. There's the right side of the union. So it's just the exact mirror of this. We're gonna produce as many A's as we want at the beginning. Once we're done producing A's, we're gonna transition to another non-terminal that produces the same number of B's as C's, recursing in the middle. So we can now derive two. We're gonna combine this with a single production that says we can allow us to go either the left side or the right side. This is kind of non-determinism at work, but it works out in that we decide from the very beginning whether we are producing the left side of the union or the right side of the union. The unfortunate reality is during runtime, can we make any claims about this? We are reading a string and it starts with an A. We need to make a decision when we see this A, whether we're going into S1 or S2. How do we make that decision? It has to be non-deterministically, because otherwise we have to search down each path and say, can we generate this via one side or the other side? So we need some kind of search. We don't know at the beginning, and we see how this is naturally ambiguous. We can attempt to produce this string and one side or the other side. And if you end up with A to the N, B to the N, C to the N, then you could end up going down either. And either one would work out with regards to that process. So we have two different derivations for that particular string. And because there are two different derivations for that particular string, the grammar has to be ambiguous. And it turns out that there's no way to rewrite this grammar in a way that's not ambiguous. And the way that you would know this is by saying, given the first symbol is an A, which path do we go down? There is no way to know that at that point without reading further into the string or doing some kind of meta-analysis on the string before starting. But an automata does not have the ability to do a meta-analysis. Questions on that? Does that make sense? Any clarifications?
You
Yeah,
said this would be considered not context free.
it is context-free because we were able to make a grammar for it. So it is context-free, but it's also ambiguous, and there's no way to fix that ambiguity because to do so, we would need to know the structure of the string before parsing it, which we can't do.
So if the language is ambiguous, would it not be regular then?
This is definitely not regular, but it is context-free, but it also says that we can't write a non-ambiguous grammar for it, which means that it's going to be very difficult to parse a kind of statement that looks like this, because for some strings, we can now have two different paths through the grammar that produce that string, which is really bad if you want to introduce something like precedence, or if you want to introduce something where you need additional rules on it. So we want to apply this concept to programming languages because that's what we care to study, and it is incredibly relevant. So we want to be able to define a programming language with respect to a grammar. So of course, we looked at this in the first week, we looked at Java's grammar, but we can now define a grammar for a programming language. And programming languages are very frequently specified using BNF, back to our form, which we won't go into a ton of detail for, but in general, it just says we can rewrite this now in BNF as a way of saying any expression is a term followed by an expression plus a term, and a term is a factor followed by a term times a factor. We have our terminals now for plus and times for precedence. And anytime we have non-terminals, they're just surrounded by the open and close angle brackets. And the arrow that we've been using, we just have now colon equals to say defined to be. And this is just BNF, how frequently programming languages are specified, but it's the exact same idea. We have non-terminals, we have terminals, and we have the ability now to construct productions out of those. instead of using capital letters like we've been doing, we use variable names or words, something that tells us what the purpose of that non-terminal is. So we can go read grammars on programming languages now, knowing exactly what this means. So let's take a look at something like this. What are the terminals and non-terminals in this BNF expression? This BNF production, I should say. Yeah.
While is a terminal, everything else is.
Yep, while is the terminal, and that makes sense, right? If you see that exact word, that doesn't have meaning by itself. If you just type while into a program and nothing else with it, there's no meaning. You don't know what you're doing. You just know that what follows are the declarations that will tell us exactly that a loop is coming. And according to the following expression and statement, that will tell us how many times this loop iterates via some kind of meta-analysis. But when we see that term while, it just tells us what to go look for next. In fact, it looks so nice that it could be a simple grammar production. You have the terminal followed by two non-terminals. And if we think about how keywords work in programming languages, we get to see things like, one, it's nice if you're reading it because it tells you what to expect, what's coming. Makes the compilers work a lot easier. We just saw one that was not a simple grammar production. So now the question that I might have, what rules can we permit and parse effectively, and what rules can we not? Because we don't want to introduce any rules of the form in the following, the preceding slide where we had that ambiguity. So we need to come up with particular kinds of expressions that we can parse efficiently. This is why we have the restrictions in programming languages that we have. And we're actually going to come back to this at the end of the course to talk about LL and LR grammars, because this is what tells us not just what we can parse, but we can parse efficiently or effectively in ways that if we construct a programming language like that, then we can analyze it efficiently. So this was a hint at what is to come. Maybe you'll ask another broad question. What general aspect of a programming language can be modeled by a context-free grammar? What does the utilization of a grammar, what does that allow us to answer yes or no to?
Regularity.
Regularity? Context-free grammar is for a context-free language, so we can determine whether the language associated is context-free. It turns out that a lot of what we do in the rules that a language is built around utilize this concept of context-free. But when we throw it all together, we're actually going to get a language class that is higher than that and allows for more complicated algorithms than just the context-free languages that we'll be utilizing this for. But there's one big term that everyone in here has heard that this models very effectively.
Largely.
It's able to tell yes or no to a particular question. And it's the syntax question. Modeling a language via a context-free grammar like this allows us to be able to determine yes or no, this program is well formed.
Experts syntax error.
Yes. So we can look for syntax errors, but we can't look for logic errors, for runtime errors. All of those need further math and analysis. And we can talk about what's needed to be able to answer the semantics question in a bit. But here's an example of something that is syntactically correct, but semantically meaningless. Do we see the difference as to why this is one, syntactically correct, but two, semantically incorrect? Syntax, we see a variable type, we see the name of a variable, we see that this is an expression. So we know what we're going to be storing into. On the right-hand side, we have an expression, and we can evaluate the value of that expression. It's just that that variable type cannot store that particular variable value. We cannot store a floating point number into a character variable. So yes, it is syntactically correct. But the rule that this violates is a semantic rule, not a syntactic rule. In fact, there is no way for context-free grammars to do anything about this. We can't recognize type clashes. This is a very important part of the compilation procedure, to be able to identify, is this something that we can or cannot do? But it's not something that can be done at the grammar level. This is something we need something else to model. In general, syntax is easier than semantics, so we're going to focus in on syntax for the moment. It'd be phenomenal if something as simple as context-free grammars existed for semantic analysis, but it is not the way things work. If there was some way this simple to do it, there's nothing that says that it can't be done, but a bunch of different proposals are out there floating around. No one's really agreed on one way to parse semantics this efficiently. If you come up with that way, maybe that's how you get rich. Last minute questions on kind of the reasoning behind context-free grammars, what we can apply it for, what we can use it for. Right, what we will cover next then is the simplification of context-free grammars. And it turns out this is a much easier problem. This will feel like a breath of fresh air. In fact, it's so much of a breath of fresh air that this whole slide deck, including this intro, is 5 slides. It was really easy to throw together. So we talked about membership, we talked about parsing context-free grammars. We determined that it's a really hard question to be able to answer yes or no. Is this particular string in this language? Because if the answer is yes, we can answer that. But if the answer is no, that was a challenge. You would be parsing and creating string after string after string after string, but we needed context-free grammars to be in particular forms to be able to say there's going to be an upper limit on the number of productions that we would need to be able to go through before we would need to have been able to generate that string. Otherwise, it's not in the language. There was a way to do it. We just had to have our context-free grammars in a particular form. We're going to go into more detail about exactly what those forms are and how you can use that to answer that question, answer the membership question. So brute force parsing, that was garbage. So we needed more efficient methods for that. And so we need to do something about restricting the production construction. We said that we could eliminate lambda and not allow for strings to become arbitrarily long. So we want to restrict the right-hand side of context-free grammars. We don't want to reduce the power of the grammars, but we need to improve the efficiency of the membership question. We need to be able to answer no faster. Some rules, some ways to answer no as fast as we can, or answer yes faster. So we need to come up with some grammar transformation rules. We know we can produce many, many, many more equivalent grammars to any given grammar out there. In fact, any grammar has an infinite number of possible equivalent grammars. You just can add some useless productions. How many useless productions? Arbitrary number. So one way to transfer a grammar, we said that we don't want any left-hand side to be able to produce lambda by itself. So we can, with one simple rule, allow us to now accept the empty string. So wherever your S used to be that had an or lambda, we're going to just say now that there's a new starting non-terminal, we'll call it S sub 0. And that can go into S or lambda, and now lambda can't appear anywhere else in the grammar. And now we can accept the empty string without lambda appearing anywhere else in the grammar. We can also look at a substitution rule, and we're going to dive into what an example of this looks like. So we can say that, actually, like drawing this out is going to be a good bit easier, but we have productions of some form. We have a single non-terminal, single terminal, and then some non-terminal followed by some more terminals. We can now replace these with an equivalent rule. So let's give you an example. So here's kind of an annoying looking grammar. What is every possible production for B, but now making it in terms of A instead? So we basically want to remove this A arrow B and make everything initially, we want to get rid of B. And to do that, we really just turn this capital B into two extra productions, where this B can now substitute that. So we're just going to replace this where B is and replace this where B is. And now you see that there's no capital B anywhere in here, so these productions are no longer necessary. So that is how you can substitute to eliminate a non-terminal. You just take everywhere that this non-terminal shows up and replace it with every possibility that you can derive via that non-terminal. Then you can get rid of one of your non-terminal productions. How are you doing? Does that make sense? Kind of substitute. Should look like just about every other substitution rule you've seen in some math class. So everything after B arrow anything, no longer necessary, we can get rid of it. So unnecessary productions are something that you can start with as well. Figure out, are there any unnecessary productions here? How can we simplify this as much as possible? Idea?
Change the S to S not, get rid of the lambda production.
Okay, yeah, we could certainly factor out the lambda. Analyzing this, what's the big issue with this grammar?
Production.
Yeah, well, there is this useless A here, but what happens if we choose this? How do we ever terminate the grammar? We can't. This creates infinite recursion. So is there any string in this language that ever uses this production?
No.
No. So that is one way to think of an unnecessary production, is that every production should be necessary to produce at least one string in the language. If no string ever goes through that production, you can get rid of that production and not change the underlying language that it recognizes. So you can remove the production entirely without loss of anything else. We can just get rid of anything that has to do with A. As A capital S B or lambda is an equivalent grammar to this. To go through this process and figure it out, we now need to define a useful production. I've already spoiled it. It's used in at least one derivation for some sentence in the language. So a useless production involves going through some non-terminal that cannot derive any sentence in the language through any sequence of productions. So you can also think of it kind of like a graph. What are the sequence of non-terminals that we are visiting in order to produce some string in the language? And then are there any nodes in that graph that we don't ever visit for the production of any string in that language. If that's the case, then we don't need them. Let's give you some practice. So here are some steps for you to go through, taking this grammar. And now trying to come up with and figure out, is there any way? Like what is the simplest version of this grammar? Step one, what do we identify? Any productions that can't lead to a terminal string at all?
C.
C. Yeah, if we go from S to C, C recurses to C nonstop, infinite recursion. So we can get rid of anything that involves C. So the S arrow C production, gone. The C arrow ACB production, gone. So from step one,
We never use the B non-term.
so yeah, which productions cannot be reached from the start non-terminal? There's no S arrow anything in any order that allows us to get to a B. So S arrow A capital S just loops, recurses back on itself. S arrow A arrow, there's no way to get to a B. So you can draw something like a dependency graph to show this. Something that shows that S can reach S can reach A terminates, there's no way to get to the B. So we can now eliminate this production based on rule number 2. So those 2 rules are everything. That's it.
Well, can't you substitute the terminal A in for the?
Oh yeah, you totally could substitute. That would lead to something that is, but now you get rid of all of the useless productions that can't derive anything in the language.
I
It's just- Yeah, there are still roads you can go to simplify to say that we can just backtrack that to there. This should just be that. And it's still simpler. But at least now there aren't any productions in there that can't generate at least one string in the language. Right. I said this would be easy. That's it.
That's the whole slide.
That's the whole slide deck. Grammar simplification is not a very hard problem. Really, it's just these two steps.
That'd be amazing.
It's probably gonna be a bunch of layers.
Hopefully we get a lot of those. So then
A
that's one I'll do on the-
Sorry.
So going from simplification, the last really important thing to do with grammars is to talk about what forms of these grammars exist and for what reason. So we need ways to study what are the regular ways that grammars are expressed to be able to better answer the membership question in general. So we're getting into, this is the slide deck you're going to want to refer to when we talk about our first programming project, because that is going to come from this material. So we know that we can now convert grammars into other equivalent forms, simpler forms, more complicated forms. You can put in useless productions in order to make it a different grammar, even though it would represent the same language, but there are an infinite number of equivalent grammars. Some of them have names and are used very frequently for some process. The first we're going to talk about is CNF, Chomsky normal form. Anyone heard of Chomsky normal form before?
I heard of Chomsky the gnome.
I've heard this.
Yeah. Noam Chomsky is very well known. Also one of the coolest last names in the history of computer science. So as long as you can take out a lambda from a grammar, which we've already shown you can always do, then there will be an equivalent grammar in CNF. CNF, kind of like how we did with regular languages, places restrictions on exactly how the productions are formed. But it is very straightforward in a way that we can now do this conversion. And it's not too bad. So we'll go over exactly how to do that because CNF is incredibly important for the membership problem. We will come back and talk about GNF, Greibach normal form. So there's also an equivalent grammar in Greibach normal form. And GNF, same types of restrictions, exactly how terminals and non-terminals are there with respect to each other. And not quite as straightforward, we'll only focus on the theoretical results. We're going to dive into CNF to start, because this is incredibly important for a lot of results that we actually use for compiler construction. So a context-free grammar is in Chomsky normal form, as long as we allow for two different forms of production. The first is a non-terminal arrow exactly two non-terminals, or a non-terminal arrow a single terminal. These are the only two production types that are allowed. None others exist in CNF. Which seems really strange that any grammar that you could write to recognize a context-free language can be rewritten in this form. How do we know that? Let's get a little practice first. Last thing we'll do today, write some grammar with at least 4 productions adhering to CNF.
Is that exactly 2 non-terminals?
Yes, it's exactly 2 non-terminals. No more, no fewer. There is a 4-rule CNF grammar. We will pick this back up tomorrow and talk about the actual conversion rules as well as what we're going to use it for. And we will dive into a longer and more complicated algorithm that we can use to answer the membership problem, which is quite exciting. Because the membership problem is incredibly important. But I'll see you tomorrow for that. I have office hours starting now. If anyone has any questions about getting started on the homework, any progress you've made on the homework?
You talk about ambiguous grammar, but then you mentioned meta-analysis to determine if it's like breaking semantic rules.
Yeah.
What about programming languages that have like, I don't know what they call it, where you like just say let this thing and then it like infers it's like,
Oh, yeah, yeah.
is that what it?
So that's very similar to semantic analysis, where you're going to wait until runtime to determine what does this need to be. All right, it's what it needs to be. So kind of like I'm gonna say this is A plus B. What is the type of B in order to do that? Well, if Yeah, something like,
Yeah, too bad. Yeah.
can you say something like, is this something that we can?
I mean,
No,
yeah.
but if we don't know the value of this, if we haven't declared that this is an integer, we can now analyze this and say the result of this expression must be a double. So if I say something like A equals this, then my analysis of what type this evaluates to, we're just gonna shove that into this. And now wherever our lookup table for A is, instead of saying that lookup table, that's whatever the user defined it to be, we are now going to figure that, all right, A represents a double.
And that just takes a way more complex compiler to do.
It actually usually isn't done via compiler, it's done via interpreter, if you're gonna do the real time. Yeah, so talk about the difference between compilers and interpreters later on as well, but yeah, one of them is kind of a one-stop, analyze the whole program. And then spits out yes or no, and the other is gonna go line by line and kind of tell you where things went wrong, right on the line that it went wrong, as it was trying to convert line by line.
Sounds like Java.
Java is usually compiled. But Python languages that like to do this are usually in Java.
Yeah, that's what it is.
So it's